Hi, and welcome to our second part on multi-target prediction methods. So we covered a bunch of pretty simple algorithms in our first part, so here I want to extend this a little bit. I will not go into the details of each and every method, but I will explain the underlying principle, hopefully well enough so that you can follow along. So we'll talk a bit about kernel-rich regression, how to handle graph relations and targets, about probabilistic classifier chains, and last but not least, a little bit about low-rank approximations for our matrix, for our numerical and matrix of target features. So I guess, we have to look directly into the methods. I guess that will make it a little bit easier. So as I've said, the stuff is a little bit more advanced, but let's see. So let's start out with kernel-rich regression. So in multi-target prediction, we quite often like to use kernel methods, or like to talk about exploiting similarities, modeling similarities. Kernels are not the worst tool for that because they measure exactly that, right? So I guess most of you who are listening into such a more advanced lecture will have heard about kernels. So you probably have heard about them either in the context of support vector machines or maybe also with regard to Gaussian processes. And you know that kernels are kind of a generalization of a dot product. They are specifically also in GPs, they are kind of used to, they are sometimes also called covariance kernels. So they measure somehow the similarity between two vectors. And we usually, for these types of ML models, we apply kernels in the feature space. So we say something like, hey, if the similarity of a feature vector x and a feature vector x dash, if that's kind of high and if that's measured by our kernel, then probably the output of these two guys should be somehow similar. So here we could now look at a pairwise model representation of our multi-target problems. So we could look at something like f of x comma t, where x are our inputs and t would be our targets. And this would be represented here by this formula, where we would have some feature mapping, some feature extraction phi, which would work on our feature vector x, and we would have this guy here, which would be a feature mapping for our target features, and then have a Kronecker product between these two guys in the model. Now, what we can also do is that we can now, as we usually do this, so we can now try to substitute these or associate these feature mappings with kernels. So we're going to need a kernel now for our feature space, as we do this for support vector machines or Gaussian processes, but we also need an associated kernel for our feature mapping for the targets. So in a few seconds, I'll now use A, as usual, to represent this kernel here on the feature map, or associated with the feature map, and I will use G for the kernel associated with our target map. And what we usually do with these types of risk minimization problems is that, and models is that we can handle them in the primal, can also kernelize them in the primal, but very often we handle these things in the dual. So if we now look at what happens with this Kronecker product here and we kernelize it in the dual, we'll arrive at this resulting formula here. So this is again, in a certain size, we are summarizing this here fairly roughly, so I guess I haven't even really written down the risk minimization problem. Then this would be dualized, and at the end, we'll end up at something like the representer theorem for support vector machines, so we can get a representation again for our model F here based on the kernels. In this instance here we have two, so you can see these kernels, so K acting between a pair of feature vectors x and x dash, and G acting between a pair of target vectors t and t dash. And here we have these dual parameters, which we now have this linear combination of these pairwise expressions here. So in order to predict a value for x comma t, I have an output for this. So we now compute that based on kernel-wise comparisons with many other points, potentially all points in the data set, and we can make this sparse as in the support vector machine, and then this would only refer to a sparse set of points. Let's maybe keep it at that. And our risk minimization problem would then look like this, which now helps us to determine here these dual parameters. So this technique is, if you want to take a look at a more in-depth look into that, here we've given you a reference from about 5 years ago. This is very commonly also used in zero-shot learning. I think I don't want to go into further details here. Let's maybe keep it at that level. Another thing that's pretty common in multi-target learning problems is that we have further prior knowledge going on for our targets. So very often, especially if we have like many targets, we do know that there's a certain, hierarchy or relationship going on between the targets. So we either know something like, hey, for this target here, there's a bunch of other targets that are kind of tightly related with it, or that have more to do with that target than other targets. And this would then be represented usually as a graph, as you can see here on the left-hand side. Or sometimes there's also a certain hierarchy going on. So maybe some of these targets are more like general, and then we have like subcategories. And this is then very often organized in a tree. And maybe what we would like to do if we run our multi-target learning program, if we perform our risk minimization for our multi-target prediction model, we'd like these relationships in the target space to be reflected and respected. And one way to do that is to work with regularization and to kind of regularize the model in a sense that exactly these types of neighborhood relations or these hierarchies are respected. Well, I guess here we'll talk a bit more about hierarchies later here. I'll mainly talk about respecting like the neighborhood of targets, so that if a target is in close relationship to another target, then probably the parameters associated with this target, with these two targets, should be similar. And what we could, for example, do, and we can do this also for more complex models, but let's keep it simple here. So if we would use a simple linear model, as we've discussed before, so we just write this down in matrix notation, and here we would have a predictor which not only predicts one target, but which predicts all targets simultaneously. So we have one theta vector associated with each target. It's just like, if we have, I kind of forgot my symbol for that. I guess it might be L. So if we have L targets, then we have L theta vectors, and we can just put them on in an n times theta matrix here. Sorry, n times L, I guess, and this will be capital. This will be capital theta here. So, and here we'd have a feature matrix capital phi. So if we now do phi times theta, just that through a linear model, or through actually L linear models, will just predict all of the targets simultaneously, and then put a Frobenius norm on top of that here. So just a fancy way of saying, let's do an L2 loss for all of these targets, and then sum up all of these L2 losses. So this Frobenius norm will simply compare the capital Y matrix of true targets, and I guess I should say that they're supposed to be all numerical here, so I guess it's something like multi-target regression usually, and we compare this with our prediction matrix, which would be Y hat, and now for every entry we compare the squared residual, sum all of them up, and that's our loss. Now, we did that before, so that's in a certain sense boring, or, well, maybe not boring, but we knew that before, discussed that before. What's more interesting now is, can we make this linear model respect these relationships from our prior knowledge and represent it in these types of graphs? And the answer is yes, we can do that. So we'll write down a regularization term, a penalty term for that, where we now iterate over all of these targets, and for each target we say, well, for each target we take a look into our graph and we extract the neighbors for that target, and then we say, well, our parameter vector for our current target under consideration should be quite similar to all of its all of the parameter vectors of its neighbors. So we just compare that with an L2 loss, or maybe I should just say L2 penalty, to all of its neighbors. So maybe I should make that concrete. So I guess, I don't know. Yeah, not sure whether, let's disregard that our graph here actually has directed edges. Let's maybe just pretend they are undirected. And I would be looking at this guy. So we would now construct the regularization term where I say the parameter vector of this guy here should be pretty similar to this and this guy. So I'll measure the difference, yeah, let's say to theta of this guy and theta of this guy here, and then sum them up. So I would have two of these L2 terms, and I would do that for every target in my learning problem. And can also extend that, so maybe I have certain numerical weightings available, could put them guess on the edges. Yeah, so if I know some things are more strongly related to each other, so I could have like a weighted graph with edge weights, and these could be respected in the regularization as well if I want to have a more fine-grained control and have more prior knowledge available to me. And this I can pretty simply optimize now, and that's quite flexible. I can really use that to respect my prior knowledge. And of course, this is, I guess, quite heavily related to this principle of the target mean regularization, which we discussed in the previous session. Here's a further way to work with hierarchies in multi-label classification. So as you can see, some of the techniques are a bit more geared toward classification. Some of them are a bit more geared towards regression. So here it's more about classification. So we have a multi-label classification problem now in front of us. And our labels are now organized in a hierarchy. So like I said, very often we have like pretty general labels here on these upper levels, and then like subcategories going down, or subcategories becoming more and more, I don't know, precise, detailed, fine-grained as we move down along this tree here. And so how do true labels and predictions now look like? Well, that's not that difficult. So it's multi-label. So each label, the ground truth and the prediction, is going to be a 0-1 thing, right? So it's a bit. It's either on or off. And on the left-hand side, let me remove a few more of my scribbling. So on the left-hand side here with the ground truth, you can see which of these labels are active for a certain observation. And here you can see the prediction. Now the interesting question is, how do we now measure this difference in a reasonable manner through our loss function? Of course, we could just compute now, I don't know, something like the 0-1 loss or any of these other functions that we have discussed. On the other hand, probably we do care a little bit about where mistakes now happen in the tree, and we kind of want to respect this hierarchical thing here. So there is something that's actually called a hierarchy loss, which is not so hard to define, and this is pretty common in multi-label classification problems, because very often in these multi-label classification problems you have, especially if you have a huge space of targets, then you do have this hierarchy information available to you. So it will look like this. So it's going to be, so we construct a sum now, and we iterate over all of the, well, let's say entries of these two trees, where our prediction and our ground truth do not match. So it's a loss function. We are only interested in the elements where errors actually occur, but we will not sum up all of these errors. We will only sum up errors where the ancestors of the cell, so I guess in a tree, this is going to be a single one, do agree. And the reason for that is we do not want to count an error if we have already done something wrong in prediction further up above. We do want to count an error if it's kind of if it appears in a certain sense for the first time in the path down the tree. So I guess it might make sense now to do this here on this example. So we could, for example, now again remove this a little bit, clean this up a bit. So we could start by comparing this and this guy. So these two guys do not have any ancestors, so we don't have to do anything, but, well, they match anyhow, right? So I guess just by looking at this guy here, we're not interested in them. So, well, I guess let's maybe do this a little bit more efficient. So fortunately, I've already marked the elements here where there seems to be a disagreement. No, actually, I've not done this. So maybe let's do this slowly. So let's look for cells now where there is actually disagreement. So these two guys here, again, so I guess maybe let's give them a little check mark. So again, they are the same. These two guys now here, if we look at them, they actually have mismatching labels. So prediction is different than the ground truth. Now, what about their ancestors? Well, their ancestors, they actually coincide. So we would count that as an interesting error. And this is also why I have marked this cell here. And maybe we can now check this for the other marked boxes. So we have this guy here, and we have this guy here. And again, if you check the ancestors, there you have a match. And then we have this guy here, and we have this guy here. Predictions do not coincide for that specific cell, but for the ancestors, again, prediction matches ground truth. So we would count exactly these three guys. What would be a counterexample? Counterexample would be this guy here. Here, yes, prediction and ground truth do not match, but we already produced an error on the previous path to that node. So we are not counting that because it's not the first instance. And what we can also do is we can put weights before these comparisons, and usually these weights are based on how far are we down in the path. So I guess if an error really happens happens further up the tree, then we do care about this a bit more. And then when we do kind of then we do an error regarding the detailed categorization further down the tree. And this can be designed, again, based on prior knowledge as you want. Another technique, again, more for classification, probabilistic classifier chains. So here we very often want to produce a probabilistic model. So we want to model this joint, or this conditional, this joint conditional distribution. So joint in the sense that we want to model the conditional distribution for all of our y's, so for all of our targets, conditional, as usual in ML, on our feature vector x. So how can we do that? So the first thing we can notice is that, well, we have all of these y's, it's a vector, this is annoying. Can we break down the complexity of that thing? We can do that even without losing anything, but just applying the product rule of probability. So we'll write down, so we will now always condition on x, so that will not change. That's just a feature vector. What we will do is we will now write down something like the density of y1 times the density of y2 given y1, always conditional on x, which I will now just leave out of laziness. And then times density of P of y3 given x1 and n2 and x2, and so on, and so on, and so on. You can also see that we can do this in different orders. And this is actually kind of, I'm not sure whether I want to say an open problem, but an interesting point, how to construct kind of an optimal ordering for this later on, when we really, by using this product rule, we use that to build up our probabilistic classifier chain. But now let's just assume we pick a certain order, which is hopefully okay for us. So, and what we will now do is that we will now, for all of these elements here in this probabilistic product, we will learn a probabilistic classifier. So that means that we will now learn a classifier that is supposed to estimate the output probability of the class for target ym based on the feature vector, but also based on some of the other targets, so in this case y1 up to ym. So I guess we can always write it like this here, just I guess we can also permute the targets before and then choose a permutation that works best. Yeah, so let's just assume that targets are in a kind of reasonable order. So we will now always kind of construct the chain like this here, right? So where we start with y1 and then we do y1 based on y2 and then y3 based on y2 and y1 and so on. And these things we will now learn independently. So how can we actually learn that? Well, we have a bunch of probabilistic classification algorithms at our disposal, I guess, maybe even too many, so we could now, don't want to go into like things like AutoML now and to search over them. It's definitely possible, but just pick a class. I don't know, we'll use something like a random forest or whatever for this. But what about this stuff here? What about this conditioning? Well, we will give that probabilistic classifier also the targets here, y1 to ym minus 1 during training. And it's now an interesting question whether we actually give the classifier access to the true labels or whether we will give it access to estimated labels, maybe from cross-validation. And the second thing might be a little bit more robust and realistic, because during prediction time, what we will do is we will enter here the predictions from the previous systems in that chain. And maybe it's a little bit easier now to look at this here. So we can now do inference in this. So what we usually want to do at the end is we want to find this. Well, maybe let's write down a probability tree here. So we have, for example, here now our feature x, and now we can look at these paths, right? So the probability of y1 being 0 given x. So this would be predicted by our first model in this chain, where we do not have to rely on any additional targets, and we can compute that. And we can also do this for the counter probability of y1 being 1, which is just the counter probability. And a bit more interesting it becomes here if we go to the second level. So here we will predict the probability of y2 equals 0, but now based on y1 equals 0. So for this, we would now access our second classifier in the chain, and we would not only give it access to x, but also add to this guy here, and this guy would have to be estimated from our first guy. Okay, and by now looking at this probability tree, we can now actually do inference on this. We can compute different stochastic properties regarding the label distribution, and we can definitely also compute this guy here, which would simply be this conditional joint, what we're interested in, and we can do an argmax. So if you look at this, you can kind of compute now path probabilities down this tree. So for example, if we follow this path here, so until here we have a probability of 30%, but then for y2 being 0, given that we are in this path here, this probability might also be 0, which we can see here, and then the probability for being on that path is of course 0 as well, because 0.4 times 0 is 0. We can do that for this guy here, go down again, get this probability for this path, and then 0.36 here. So and if you were to look at that, I guess that is going to be the maximum. So I guess that would be our argmax. And we can compute also other marginal distributions or even conditional things regarding the labels by exploiting the structure of this probability tree, which is quite nice. This is also a pretty nice model agnostic technique. So I usually like these things because you can build on top of stuff that's already there. So you can kind of bring out your existing machine learning toolbox, which gives you access to a bunch of different probabilistic classifiers. And then you can start implementing stuff like this here usually pretty quickly. You have access to already pretty stable and established algorithms. You can do AutoML by optimizing over them, using established hyperparameter optimization techniques. So you don't really have to start from scratch, and you can really build on existing work. That's usually quite nice. Last topic I'm not sure what I should say today. Depends on how many videos of these you watch in a row. For me, it's going to be the last topic of today, because I'll go home after this, would be low rank approximation. So what we now want to talk about is, again, this is more, I guess, suited for multi-target regression. So let's assume that we have that. So we have our matrix Y here. And maybe again, we use this, we assume it's, I guess also this is geared towards problems where we have a huge number of targets. And because of that, maybe we have to use a simple linear model. And again, we have here our Frobenius norm formulation. An idea to kind of regularize this further, maybe also run it computationally more efficient and exploit structure that's shared across targets, we could now say, how about how about a low-rank approximation of our parameter matrix? That might be quite nice, and kind of a less formal way of writing that would be like this here. So can we actually do a low-rank approximation of this? And the answer is yes, of course we can do that. There are quite a lot of tools available for this. For example, something like an SVD decomposition. So how would that look like? So we would have our parameter matrix here. Dimensionality would be P times L. So P, number of features, and L is just number of targets. And we can now assume, so if you would assume a low-rank structure, this usually looks like this, right? So this would be potentially also how an SVD decomposition looks like. So we have this matrix here, which has a rectangular structure and more rows than columns. And we have this V guy here. And then, of course, if you look at these two guys can never have a rank that's larger than 2, right? So if we multiply these two guys together, we have our matrix A here, which has 4 rows and 6 columns, but A cannot have a rank larger than 2. So this will be a low rank approximation of our A, and we can now ask for a matrix. So we can now ask for a matrix of with a certain rank that's not too high, which nevertheless approximates another given matrix quite well. So we can, for example, say we want to have a matrix that represents here our phi, but which follows this low rank decomposition. And then phi times x, which will be our prediction, is going to be u times v times x, right? And we can now solve that. So there are established tools for this, and also we can now put further regularization on top of that if we wanted to. So we kind of combine these things with all of these other things we have learned about mean target regularization, or even these graph regularization techniques and so on. And this again can make everything computationally a bit more efficient.